Hi everyone, in this video we are going to learn how to represent the relation using diagram, or we can say that how to draw the pictorial representation of the relation. After that we will learn how to identify the type of relation from the pictorial representation of relation. So starting with how to construct that, the first step is always find the element of the set. As the relation is defined on a set, count the elements in a set and represent all such elements by a point that is also called as the vertex or node. Then look for the relation. In relation you will get an ordered pair, and each ordered pair is represented by a directed edge. Now what do you mean by this one? Suppose we have 2 points in a set, that is A and B, and the ordered pair AB is a part of relation. It means we need to draw this one by a line with the direction that is given by an N. So we will say that A is related with B by making an edge that starts from A, ends at B, and this is called as a directed edge. When we have a directed graph that consists of some vertices together with set of edges, this is called as diagram. That's why we are saying that representing relation using diagram, because it is a directed graph that consists of the edges with the direction on it. Now let's understand with the help of example. Suppose we need to draw the directed graph of this relation that is on the set A. In set A, we have 4 elements. So first thing is we need to take the 4 points. So it is up to you how to draw these 4 points in a plane. So right now I have taken the 4 points like this way. So this is the first point. Name it as a 1, 2, 3, 4. We have labeled with the help of the elements in a set A. So elements are 1, 2, 3, 4, and similarly we have represented here elements as 1, 2, 3, 4, or we can call it as a vertices. Now we need to draw the edges as per the relation. First ordered pair we have 1, 1. It means 1 is related with 1. As per the edge, we need to start an edge that starts from 1 and ends at 1. Put the direction on it. This is called as the loop, or we can call it as a self loop. An edge that starts and ends at the same point is called as a self loop. Due to this ordered pair, we are getting this loop. Next we have 1 is related with 2. Means we will put an edge that starts from 1 and ends at 2. 2 is related with 1. So put an edge that starts from 2 and ends at 1. Put the direction on that one. 2 is related with 3. So take an edge that starts from 2 and ends at 3. Then 2 is related with 4. So take an edge that starts from 2 and ends at 4. Then 3 is related with 1. So take an edge that starts from 3 and ends at 1. And the last ordered pair is 4 is related with 3. So this is the final directed graph of this relation on the set this. Let's take the another example. In this case, we need to list the order of pairs of relation represented by the directed graph this. So here we have 4 vertices, and the name of vertices is A, B, C, D. It means in a set A, we have 4 elements and they are A, B, C, D. Now we need to write the relation that is defined on this set according to this directed graph. So we will start from the edges. So this edge indicates that A is related with B. It means relation contain the ordered pair AB. This edge indicates that edge starts and ends at the same point, that is B, means B is related with B. This edge is B is related with C. Here C is related with D, and this last edge indicates that C is related with A. So there are 5 edges. It means there are 5 ordered pairs in the relation R. Now with the help of directed graph, we can identify the type of relation. Suppose we need to identify the reflexive relation, whether the given directed graph represents the reflexive relation or not. Reflexive relation means every element is related to itself. Every element is related to itself means there is an edge that starts and ends at the same point. According to this, it means we can say that having self loops at each node indicates that the relation is reflexive. On the other hand, irreflexive relation means for every element of the set A, ordered pair A should not be a part of a relation. Means there should not be any self loop on any node. So for the irreflexive relation, we can say that having no self loop on any nodes indicates that it is a irreflexive relation. Whereas in a symmetric relation, we say that the order pair AB, if it is a part of relation, then reverse should be there. It's like if there is an edge from A to B, then there must be a second edge that is from B to A in opposite direction. So from the directed graph, we can say that the relation is symmetric if and only if for every edge between distinct vertices in its diagram, there is an edge in a opposite direction. मीन्स अगर एक डायरेक्शन में एज है तो ऑपोजिट डायरेक्शन में भी एक एज होनी चाहिए. On the other hand, in case of antisymmetric, if the ordered pair AB is a part of relation as well as ordered pair BA is a part of relation, then both are same. Or we can say that if AB is a part of a relation where A is not is equal to B, so this implies reverse should not be there. It's like if there is an edge from A to B, then reverse edge should not be there. So in general, we can say that a relation is antisymmetric if there are never two edges in opposite direction between distinct vertices. Moreover, self loops can be there, means such type of elements can be the part of relation. And in case of asymmetric relation, same thing we are saying that reverse should not be there, but the change is self loop is not allowed in the case of asymmetric. Condition is same. There never be a two edges in a opposite direction as well as no self loop as a part of directed graph to call it as a asymmetric relation. Let's check if directed graph indicate what type of a relation. So here we don't have a self loop on A, so it means it is not a reflexive relation. Whether this is a irreflexive relation? No. Why? Because there is a self loop on the B vertex. Now whether this is a symmetric relation? No. Why not? Because if there is an edge from A to B, there must be an edge from B to A, and that is not there even in the other cases as well. Whether this is a asymmetric? No. Why not? Because there is a self loop, and self loops are not allowed in a asymmetric. Now antisymmetric, let's check it. Self loops are allowed and exactly one edge is between the distinct pair of vertices. So clearly this is a antisymmetric. So with the help of diagram, we can easily predict the type of relation.